Einstein's theory of general relativity has revolutionized our understanding of the nature of space, time, and gravity. It describes gravity as the curvature of spacetime that is caused by the presence of matter and energy, both. And the foundation of this theory lies in what is called the Einstein-Hilbert action. The Einstein-Hilbert action describes the curvature of spacetime in the presence of matter and energy. From this action, the Einstein-Hilbert action, Einstein derived the field equations that govern the curvature of spacetime. Now, in this video, we'll provide a comprehensive overview of the derivation of these field equations. We'll start from the variation of action with respect to the metric tensor, and we'll then arrive at the final form of the field equations, following a step-by-step procedure. We'll also emphasize the underlying physical concepts and mathematical techniques. We'll also demonstrate how Einstein's field equations will then reduce to the well-known Newtonian gravitational equation in the weak field limit. Since Einstein's field equations are a more generalized version, it is very important that they, under some conditions, reduce to what we all know, what a basics physics course teaches you about gravity, which is the Newtonian's gravity, right? So that is supposed to happen. It is a must. Now, in Newtonian's gravitational equation, in the weak field limit, the gravitational field is small and the space-time curvature is weak. Now, that is relatively, right? So, for example, for Earth, we can assume that this gravitational field is much smaller compared to some massive object, compared to, suppose, the sun or even a whole galaxy, a black hole, and these type of other objects. So this video is intended for physicists or students, even researchers who wish to deepen their understanding of the theory of general relativity and, of course, its implications for our understanding of the universe. So we're going to start our discussion with the field equations from the Einstein's Hilbert action. So that's the first part of this video, to derive these field equations using the Einstein-Hilbert action. That's also how Einstein did it. Now, we're going to first start with the Einstein-Hilbert action, right? So I'm going to write this action down. It is S is equal to 1 over 16 pi g times the integral d4x square root of minus g and r. Like this, right? So this is what we call the Einstein-Hilbert action. S is obviously the action. G over here is the Newtonian's gravitational constant. It is just the gravitational or the universal gravitational constant. d4x, this element that you see, the differential element, this is the four-dimensional volume element, right? So it includes both space and time coordinates, the x, y, and z spatial coordinates and the time coordinates, all together making a four-dimensional volume. G over here in this equation is the determinant of what is called the metric tensor. And the metric tensor is written as G mu nu. So it has these two indices and the letter G. This thing is called the metric tensor. And once you have the metric tensor, that means that you have now specified your geometry of spacetime, right? Okay, now what is left is this R. And this R is what we call the scalar curvature, right? All right, now we're going to start varying this action, right? And so the variation of this action with respect to the metric tensor, that is delta S over delta G mu nu, is equal to, it's 0, right? Since you don't see a G mu nu explicitly in this expression. However, what we can do is we can compute the variation of this action with respect to the metric tensor. We can do this in this way, that this is the condition for the principle of least action, right? So you use the principle of least action to derive your equations of motion. And in this case, those equations are the Einstein's field equations, right? Okay, so what I'm going to do now is I'm going to vary the action with respect to the metric tensor G mu nu. Now, we are going to do that as follows. So this is delta S over delta G mu nu. By the way, again, this is the condition of least action that gives you your equations of motion. Right. Okay, so let's continue. So delta S over delta G mu nu is just equal to delta over delta G mu nu. What is S? Over here, it is 1 over 16 pi G integral d4x square root minus G and R, right? So I'm going to write that down exactly over here. Now, what we can do is we can take this this derivative inside, right? Since it's not going to act on this constant, right? And it's not going to act on the differential volume element, obviously. But what it will act on is this term over here, because this G and R are implicitly the functions of G mu nu, right? So they come from G mu nu essentially. So we can write this thing as 1 over 16 pi G integral of d4x delta over delta G mu nu of square root minus G times R, right? So this is what we have. Again, this differential, this differential operator, or this change with respect to G mu nu is acting on this thing, square root minus G times R. So what can we do next? We can definitely use the product rule of the differentiation, and we can expand this term, right? So which one? This term. We can expand this thing by applying the product rule of differentiation. All right, so let's do that now. Let's go a bit down, and we know that this thing is delta over delta G mu nu minus, square root of minus G times R. Now, as I have said, that G and R are basically the functions of G mu nu. That is why we are applying the product rule over here, since both of them depend on this variable of differentiation, which is G mu nu, right? So the product rule says that, okay, first of all, we can take the square root of minus G as it is, and then differentiate R with respect to G mu nu. So that is delta R over delta G mu nu. Okay, what's the next step? Plus the next thing. So now we are going to take R as it is and differentiate the square root of minus G. So that's delta square root of minus G over delta G mu nu. Okay, all right. So we're getting somewhere. Now what we're going to do is we are going to use the contracted Bianchi identity, right? So the Bianchi identity, which you might be familiar with if you have taken general relativity, a course on general relativity. In fact, you must be familiar with it if you have taken a course on general relativity. And obviously, if you are watching this lecture or this video, you probably have an idea of general relativity, and then you might have heard of Bianchi identity as well. However, I'm going to write this down, and we need this to simplify this term on the right-hand side, this one, right? So I'm going to, again, perhaps highlight it. So we need to simplify this term. So we are going to take the advantage of the Bianchi identity, basically the contracted Bianchi identity, which is del mu G mu nu is equal to 0. Now, you might be asking, what is G mu nu? Or perhaps you know what that is. G mu nu, this thing, is known as the Einstein's tensor, right? So this G mu nu is the Einstein's tensor. Now, what is Einstein tensor? Einstein tensor is simply G mu nu is equal to R mu nu minus 1 by 2 G mu nu times R. So you can see it is made up of the metric tensor, right? Now, over here, what we are going to do is we are going to take the covariant derivative of this G mu nu by using this thing. The Bianchi identity says that you take the covariant derivative of G mu nu, and that should equal to 0. That should vanish. So let's do that. Let's take the covariant derivative of G mu nu. Something like that, right? So once you do that, we're going to also use the fact that the covariant derivative commutes with this variation, delta over delta G mu nu, right? So if it commutes with this variation, and taking the covariant derivative, what we get is delta mu, delta g mu nu over delta g. Now I'm going to change the indices, right, so that we don't get confused. Both of them don't have the same indices. So let's use alpha and beta this time, and this would be equal to delta over delta g alpha beta. And what we have, this thing acts on this thing. Since, as I said, the partial derivative commutes with this differential, right? So it commutes with the variation, or you can say. So this thing is variation. Anyhow, so what I can do now is I can say that this thing is just equal to this thing and delta mu g mu nu, right? So what I've done is I've brought this covariant derivative inside. But remember, from the Bianchi identity, this thing is 0, right, over here. So I can say that all of this thing just vanishes. It is equal to 0. All right, now what I can do is I'm going to expand the left-hand side of this equation, and I'm going to do that using, again, the product rule of differentiation, right? So what I'm doing is I'm saying that let's take this delta mu variation of g mu nu over variation g alpha beta, and this thing is equal to, I'm taking this covariant derivative inside, so this is delta over delta g alpha beta, the differential, the Nabla operator, or the delta. Sometimes I'm calling this delta, but I'm sure that you know that this is the name of the operator is the Nabla operator, and this thing would be del mu g mu nu. Right, so that's the first term. This next term would be that I'm going to take my g mu nu outside, and then I'm going to take the derivative of the rest. So that would be this Nabla operator times delta over delta g alpha beta, right? Okay, so this is what I have, all I've done so far is apply the product rule of differentiation. Now, what is this equal to? This would be equal to delta over delta g alpha beta. Now, you can see that I can write this as delta, or the Nabla operator, g mu nu, this thing, and then plus, now I can take g mu nu outside, and I can write delta over delta g alpha beta of the operator, the Nabla operator, right? So that is delta mu. Okay, all right, so now what we're going to do is we'll use the fact that the variation of the metric tensor vanishes at the boundary of space-time. So I'm going to write this down as well. Now what I'm going to do is I'm going to use this fact that states that the variation of the metric tensor g mu nu vanishes at the boundary of space-time, right? Because at the end of the space-time, at the boundary of space-time, the metric tensor is not going to vary, right? Okay, so using that, right, and what does that mean? That means that I can neglect the boundary term, and I'm going to now apply the integration by parts, and what we get is, remember, we have this integral d4x square root of minus g minus 1 by 2 g mu nu delta g mu nu over delta g alpha beta. Right, so what is this equal to? This is simply your minus 1 by 2 will come outside, and in the integral you will have again d4x square root of minus g mu nu delta alpha mu and delta beta nu, right? So these are the Kronecker deltas that you see from this thing, right? So we have delta g mu nu, and so on both the sides we have the metric tensor, so we can write this as follows in this way. All right, so now what we can do is this delta, this mu contracts with this mu, and this alpha contracts with this, this nu contracts with this nu, and what you're left with is alpha and beta, but since mu and nu have been contracted, so g is left with the indices alpha and beta. So that means that this would just be minus 1 by 2 integral of d4x square root of minus g alpha beta. All right. So now what I'm going to do is I'm going to substitute all of this back in this equation that I wrote down. So I'll write it down again, delta S over delta G mu nu. And this is equal to 0, right? So I'm just going to put this back into this equation. And once I do that, what I get is, so this is the variation of action with respect to G mu nu. I'll get 1 over 16 pi G integral of d4x square root of minus g times r mu nu minus 1 by 2 g mu nu, this thing. This Einstein tensor, I'm just expanding it and writing it down over here, and times r, right? So this, all of this thing is this g mu alpha beta or g mu nu, right? Okay, so since we are only left with alpha beta over here and there are no other indices, these are dummy indices, I can just replace them back to mu and nu. So that's what I've done over here, right? Okay, so this thing, and then we have the Kronecker delta alpha mu delta beta mu is equal to 0. All right, since these deltas are symmetric under the interchange of alpha and beta, what I can do is I can rewrite this thing as 1 over 16 pi g times the integral of d4x square root of minus g r alpha beta minus 1 by 2 g alpha beta r, and this thing is equal to 0. Right, now what I'm going to do is I'm just going to do some simplifications, right? I can do one thing that I can do is I can multiply this whole equation by 16 pi g, or just say that they take the 16 pi g on the other side, since the right hand side of the equation is 0. What we would be left with is this thing over here that is inside this thing, and this would be r alpha beta minus 1 by 2 g alpha beta r is equal to 8 pi g, and we get something that is called the this thing t alpha beta. So I'm not going to go into the derivation of what is that thing that we're calling this t alpha beta. However, I'll definitely tell you what is this t alpha beta, right? Anyhow, this equation that you see over here, t alpha beta, is the energy momentum tensor, right? So it carries the information of the momentum and energy, right, inside of anything inside this space-time. What does that mean? That means that this tensor describes the distribution of both matter and energy in the space-time. Now, this equation is what we were talking about. This equation is called the Einstein field equation, right? You might be wondering, I said we'll be deriving Einstein field equations, right, the plural. However, that is exactly actually what we did. Since this is not just one equation, these are many equations written as a single equation. Right, okay, so that's the first part of the video, which we are done and dusted with. The next thing that we're going to do is to find the relation of the Einstein field equation to Newtonian gravity. And as I've said this before, this is done in the weak field limit. So to see how the Einstein field equations reduce to the Newtonian's gravitational equation in the weak field limit, we'll assume that the gravitational field is weak, right? And the space-time curvature is small. So when I say the weak field limit, that means that the gravitational field is weak and the space-time curvature is small, right? So what does that mean? This means that we can approximate the metric tensor G mu nu, right? And we can approximate this metric tensor G mu nu by the Minkowski metric plus some perturbation in that Minkowski metric. Remember, Minkowski metric is for completely flat spacetime, right? And since it is for completely flat spacetime, I can cause some perturbation in that flat spacetime to curve it slightly, right? So then the metric tensor becomes the flat metric tensor eta mu nu, which is the Minkowski metric, plus some perturbation, let's call it h mu nu. So this is how the metric tensor is modified or approximated in the weak field limit, Now you have to know this thing, that since I'm saying the perturbation is very small, that means that the mod of this h mu nu should be much, much smaller than unit or 1, right? So that just says that the perturbation h mu nu is very small. All right, now what I'm going to do is I'm going to expand the Ricci tensor and the Ricci scalar. The Ricci tensor is, by the way, this r mu nu. This is the Ricci tensor, and the Ricci scalar is this r, right? So this is the Ricci scalar. Right. So again, I'm assuming that you know these terms, what is a Ricci tensor and what is a Ricci scalar. So I'm not going to go into the detail of that, since you understand these terms before you dive into the theory of gravity, right? So you just understand the differential geometry, basically, and then you start diving into gravity, where you develop the Einstein field equations and so on, right? Okay, so now what I'm going to do is I'm going to expand this both of these, tensor and scalar, to the first order in h mu nu, which is the perturbation, right? So to the first order in the perturbation. And that is done by saying that r mu nu, which is equal to, so now I'm going to write down what this r mu nu is equal to exactly, right? So that is partial, this is the partial derivative with the index alpha times the Christoffel connection, right? This thing that I'm writing down that has 3 indices, 1 at top and 2 at the bottom, this is called the Christoffel connection or the Christoffel symbols, right? And next is minus partial nu and another Christoffel connection, that is this one. And then you can have higher orders of h, so we'll just say h, the order of h squared, right? In the same way, I can expand the Ricci scalar to the first order in the perturbation. And that is done by, so I'm going to write this Ricci scalar. How do we get Ricci scalar? By contracting the Ricci tensor with the metric tensor. So that is g mu nu times r mu nu. So in this way, you can see the indices of g and r contract with each other. Mu nu contracts with mu and nu. So what you get is, again, what you get in the first order of the perturbation is this operator. This is called the Lambertian operator, or sometimes also called the box operator. And this box operator, by the way, I'm going to write it over here, is just this thing, the partial derivative written in this way, right? So this is your box operator. Anyhow, this box operator acts on h mu mu plus higher order of h, so h squared. Right? So this is what I've done so far, is I've only expanded the Ricci tensor and the scalar to the first order in our perturbation. All right, good. Now I'm going to use these expressions and rewrite the Einstein's field equations, right? Since if you go back over here, this is the Einstein field equation. We have the Ricci tensor, and it is made up of the Ricci scalar as well. So I'm going to replace these two terms by this thing. And I'm going to replace the g mu nu or this thing by this expansion, right? The approximation of g mu nu as eta mu nu and h mu nu. So now, if doing that, this equation, the Einstein field equation, becomes, I'm going to write it down over here as box h mu nu is equal to, minus partial mu partial nu h alpha alpha. And this thing is equal to minus 16 pi g t mu nu. Okay, so what is this? This is simply the Einstein field equations written in the weak field limit. So in the weak field limit now, we can assume that this energy momentum tensor T mu nu is dominated by the stress energy of non-gravitational matter. Since the gravitational field is weak, so the energy or momentum is coming from non-gravitational matter instead of some gravitational matter which can cause curvature, right? So it is dominated by non-gravitational matter. And if that is the case, then mathematically I can write that thing as T mu nu is equal to rho plus P, and I'm going to tell you what these things are, U nu, or let's say U nu minus P G mu nu. Okay, so I've written this equation down. Again, this equation is the stress energy tensor, which is dominated by non-gravitational matter. So that is supposed to be understood. Now, in this equation, rho is the mass density of the matter. P is the pressure exerted by that matter, and U is the forward velocity of your matter, right? And then G mu nu, it is your metric tensor, right? Okay, now what I'm going to do is I'm going to substitute this expression into the Einstein field equations, and I'm going to neglect the higher order terms of h squared, right? So let's take this and let's put it in the Einstein field equations. Once I do that and I rearrange this thing, I get box h mu nu, which is this term, and then let's take all of the rest on the other side. This thing is equal to, so you would be having minus 16 pi g. Now what is t mu nu? It is this thing, right? So I'm going to write rho plus p u mu u nu. So in this expression, note that I have neglected the order h squared terms to write down this equation. Okay, so what I can do next is I can further simplify this equation. This is the modified Einstein field equation, by the way, where we are talking about the weak gravitational field. So the curvature of space-time is very small. We can further simplify this by assuming that gravitational field is also static and spherically symmetric, which is a very good approximation, by the way. And if that is the case, then the metric tensor can be written as, which is this element ds squared, right? The metric tensor can be written in this form such that this is equal to minus 1 plus 2 phi dt squared. So this is the time part of that. If you write it down as a matrix, then this would come under the t thing, plus 1 minus 2 phi times dx squared plus dy squared plus dz squared, right? So that means that this coefficient is with x, y, and z both. All right, okay, so what is phi, by the way? Phi is your usual gravitational potential. You must be familiar with that if you have taken any course on Newtonian's gravity, right? Any course, or you might have studied it in your A-levels or high school, whatever. You must be familiar with phi as the gravitational potential. Now in this case, the only non-vanishing components of h mu nu are this one. So let me write it down as h 0 is a non-vanishing component, right? Which is just minus 2 phi, and hii, which is the spatial components. Again, this ii means that both these indices are exactly the same. So if I have h1, then the other one is also 1, which is equal to h22, which is equal to h33, right? That's what this thing is. And what is this equal to? This is equal to 2 phi. So these are the only non-vanishing components of the tensor h mu nu, of the perturbation. Now substitute these components into the equation, this one, and once you do that, we're also going to use the fact that the forward velocity is u mu, which is minus 1, 0, 0, and 0 for non-relativistic matter, which is at rest. So again, this is in this way, since the matter is non-relativistic and at rest. That's why the spatial components are simply 0. Now, once we do that, we put this thing into this above equation. What we see is we obtain del squared phi is equal to 4 pi g rho. This equation is the Poisson's equation for gravitational potential, right? So this is the Poisson's equation for gravitational potential, right? And if you are familiar with Newtonian's gravitation or Newtonian's gravity, this is just the same thing as the Newtonian gravitational equation. And we can see that if we write the gravitational potential in terms of the mass density. So I'm going to do that for you now. I'm going to write the gravitational potential in terms of the mass density, which is phi of x is equal to minus integral of g rho of x prime over x minus x prime absolute d3 x prime. So this is the gravitational potential in terms of the mass density, that is rho, and x over here is the position vector, and this integral is taken over all space. So if I have this thing, and now I can take the Laplacian of both sides of this equation. So what I'm going to do is taking the Laplacian of the both sides, what I get is the left hand side is just del squared phi, and that is del squared phi of x, right? And the right hand side, we are only left with, if we take the Laplacian, we get minus 4 pi, right? And that is what we get from this, all of this integral over all space and all of this, and we're left with g and rho. So that is g and rho of x. Now you see that this thing is exactly the same as this Poisson equation for gravitational potential. Note that this Poisson equation for gravitational potential was derived using the Einstein's field equations, and so we've reduced the Einstein's field equation to the Newtonian's gravitational field equation, the Newtonian's gravity. So thus, in the weak field limit, the Einstein's field equations have been reduced to the Newtonian's gravitational equation with the gravitational potential given exactly by the same formula as you see in Newtonian's gravity. All right, now let's just quickly discuss what we have done in this video. We have shown that the Einstein field equation described the curvature of space-time in the presence of matter and energy. How did we do that? We derived the equations from the Einstein-Hilbert action. That was our starting point. We demonstrated the mathematical framework that underlies general relativity when we played around with the equations. Furthermore, we also illustrated how the Einstein field equations will reduce to the Newtonian's gravitational equation in the weak field limit. And that was highlighting the connection between classical mechanics and your general relativity. So that's how both of these things are connected. The classical mechanics and general relativity are connected in this way. Okay, all right. So let's end this video with this saying that while the derivation that is presented in this video, it provides a fundamental understanding of the Einstein field equations, the full implications of general relativity are far-reaching, and they continue to be studied by physicists and mathematicians as well. General relativity is more or less very close towards mathematics rather than physics. In physics, we just deal with the gravitational part and we are done with it. But in mathematics, you deal with all of the mathematics that lies with these curvatures, differential geometry, and all of that thing. So from the prediction of black holes and gravitational waves to the expansion of the universe and the nature of time itself, general relativity has fundamentally transformed our understanding of the universe and our place within it.